Good morning. Welcome back from spring break. So what I'm going to do today, what we're going to start with is Laplace Transform. So this is our final chapter of the semester. So the rest of the semester we're going to devote to studying differential equations using the Laplace Transform. The Laplace Transform is useful for many reasons. One is that it will help us solve some differential equations, and in fact it'll help us solve some differential equations that we might have had trouble solving any other way. But the inevitable usefulness of the Laplace transform is actually in relation to a related mathematical object called the Fourier transform. And we'll talk about the relationship between the two. The Laplace transform is kind of a special case of the Fourier transform. The Fourier transform is super useful. I'm going to include some nice, fun, intuitive links about the Fourier transform that'll just be optional material for you. But the Fourier transform is really the useful thing, especially for all of you engineers and physicists and even mathematicians. So as a mathematician, I use the Fourier transform basically, I shouldn't say every day in my research, but I use it a lot. It's probably the biggest kind of toolbox that is the most frequently used tool in my toolbox for mathematics. So it's really useful across the board for math, physics, basically any engineering. So again, that's the Fourier transform. So Fourier transform, and again, the Laplace transform is kind of a special case of the Fourier transform. So we'll talk about the Fourier transform a little bit later. I'll define exactly what it is. It's a slightly different object here, but a little easier to describe and a little bit more useful for what we're going to do right now is the Laplace transform. So the way that this Laplace transform is going to work, the way that we're going to define it, is this is going to be, we're going to have as our input, we're going to have some function, say little f of t. And what this actually is, this Laplace transform, is it's going to be the integral from 0 to infinity. So it's an indefinite integral from 0 to infinity of e to the negative st times little f of t dt. And so we're going to integrate this function f against e to the negative st. And what this is going to be, if you think about it, is that your answer is going to be just some function of s. And so what our convention is that we're going to use the lowercase letter for the input variable as a function of t, so little f of t, and then the transform is going to be capital F of s. Okay, so that's going to be our convention. So similarly, if I were to have the Laplace transform of little x of t, you will get capital X of s, and if I were to have the Laplace transform of, say, little y of t, you will get capital Y of s. I want to point out, I've not for any good reason, but switched from parentheses to brackets. Both of these are commonly used for the Laplace transform. They don't mean anything differently. Everything is defined exactly the same. So with a bracket, this would be the integral from 0 to infinity, e to the negative st chi of t dt. Okay, and likewise for the Laplace transform of y of t. Okay. So what I want to do first is I want to actually go through, I think this is actually a good point to let me tell you what the Fourier transform is. So the Fourier transform is really the heavy-duty, kind of the big tool in the toolbox for a lot of mathematical modeling, for a lot of engineering, again, physics, math, so a lot of things that the Fourier transform is going to do for us. And what it is it's a tool that's going to help us it's going to study wavelengths, basically. So Joseph Fourier was a mathematician. He found himself in Egypt on some sort of an archaeological mission, and he got so sick of the warm weather in Egypt that what he did is he developed a model for how the heat's going to disperse across whatever room or whatever whatever situation he was in. So he developed this kind of mathematical model to study the heat. And so the Fourier transform turns out to be super useful for lots and lots of things. People use it for wave analysis. So if you want to have, if you think about some sort of like musical instrument, if you're plucking or if you're plucking a bunch of guitar chords or hitting a bunch of piano keys all at one time, you get this kind of crazy sum of waves. And so the Fourier transform is going to show you how to deconstruct those waves to get back the original sources. So the Fourier transform is used a lot. It's used in basically any sort of wave analysis, so things like televisions, your computer certainly, anything acoustic or anything audio really is using a Laplace transform or a Fourier transform. So this is a tool that's very, very useful. It's hard to see how it's useful intuitively right away. I'll post a good video about it. There's one or two videos that I've seen about the Fourier transform, and I'll post those. One has kind of a graphical approach to how the Fourier transform works, and the other approach is going to be kind of, again, just a little bit more intuitive approach, and I'll post those. Those will be optional for you. Anyways, so the Fourier transform, I just feel compelled to point out, the Fourier transform is going to be denoted by capital F, so that's a capital F of, again, let's say little f of t. And what this is it's going to be the integral from negative infinity to infinity. And what you're going to do is you're going to integrate e to the negative 2 pi I x t, or we can say st, just to keep it similar to what we had before. Oops, we can keep it similar to what we had before. E to the negative 2 pi I st f of t dt. And that looks almost the same, right? If you think about these two definitions, they look, they're both improper integrals. You have this e to the negative st kind of built in. This scaling factor of the 2 pi I is just there for convenience for the Fourier transform, so that makes it so that a lot of the different properties of the Fourier transform can be written out pretty nicely. It's not really there for any other reason. And then other than that, it's basically the same, except you're going to have the indefinite integral from negative infinity to infinity rather than from 0 to infinity. E to the negative 2 pi I st, remember, is really a complex valued function, right? So this e to the negative 2 pi I st, remember just e to the I theta is cosine theta plus I sine theta. So what we're really doing is we're integrating our function f against this e to the negative st, e to the negative 2 pi I st. And so that's going to give, we're going to integrate f against cosine and sine functions. So at a certain level, the Fourier transform has to do with taking our function f and then interpreting it using sine and cosine functions. And I'm going to leave that as a mysterious comment because I want to move on. So anyway, so that's the Fourier transform. Again, this is a huge tool. We could spend a whole semester just talking about the different properties of the Fourier transform, and we could still have, you could probably spend way more than one semester talking about the Fourier transform, its utility, how useful it is for a whole variety of things. It's pretty ridiculous how useful of a tool this is. But anyways, so that's the Fourier transform. So we'll go back and we'll now restrict ourselves to talking about the Laplace transform. So what I want to do is I want to find what our immediate goal is here, is I want to build up and I want to kind of come up with a catalog of different functions where, I'm bad at doing two things at once here. What we're going to do is we're going to build up a catalog of functions, and we're going to take the Laplace transform of those functions, okay? And so we'll see, it's not immediately clear that this has anything to do with differential equations. It does, of course, but that's not immediately clear. So what we're going to have to do is develop the Laplace transform a little bit, talk about different special different functions and their Laplace transforms, and then after we're good with that, after we have a little bit of practice with that, we'll go through and we'll talk about what are the utility of the Laplace transform, how is it useful for solving differential equations. Okay, so we'll go through and we'll do that next.